In this video, I want to begin talking about the linear regression t-test. And it's a hypothesis test essentially for the slope of a regression equation. I wanted to begin with just reminding you of some of these estimators we've learned. And by estimators, I mean when we collect a sample mean, we're trying to estimate the population mean. When we collect a sample deviation, we're trying to estimate the population deviation. When we collect a sample proportion, we're trying to estimate the population proportion. Well, along with that, our old regression equations that we learned about a while back, our y-hats, these are really estimators as well. A is our estimator of alpha, the real response quantity when the explanatory is 0, right? The y-intercept. And our B, our slope, is an estimator of what we call beta, which is a true relationship between the explanatory and response variable. It's that real slope of the population, okay, that relates the two variables to each other. So this is what we're really going to be testing today, is this slope and whether it exists. To begin with, I just wanted to set up, we're going to use this data set today. I want to begin by just getting the regression equation. Let's just remind ourselves on the calculator how we do that. Okay, so remember the first thing you're going to do is you are going to go to your stat edit and put in your explanatory and response variables in list 1 and list 2. So stat edit. Then you're going to go to stat calc. And the 8th choice, number 8, is linreg a plus bx. There's another linreg in there that's ax plus b, but our book uses a plus bx. So there's your y-intercept, and there's your slope and correlation. So let me just kind of make that a little smaller, and let's just answer A right here. We are trying to predict pulse, so we do pulse hat equals 47.17 plus 0.302 times height. Remember, we use the context. Hey, B, what is the correlation coefficient? Well, R is 0.205. Now, it says interpret the correlation coefficient. Instead of that, I took this from an old book. I'm going to do R squared instead. 4% of all variation in the response variable, so for us that is pulse, can be explained by variation in the explanatory variable. For us that means height. That's not very much, right? You're hoping for a larger percentage. That gives us a much better idea that what we're dealing with is a good explanatory variable for our response. If we're only explaining 4% of the variation, that's not good, okay? Predicted pulse rate of a 67-inch tall student. So now we would simply plug 67 into our equation like that, and we get 67.4. Okay, and finally interpreting the slope. Pulse is predicted to increase by 0.302 for each additional inch of height. So let's just remind ourselves kind of the key phrasing here. A slope is what's, for a regression equation, is what's predicted to happen to the response variable for every 1 unit of the explanatory variable. So again, it's regression, so it's a prediction, right? We don't know for sure, so the pulse is predicted to increase by the actual slope for each additional inch of height. Now, what I want to move towards is doing a hypothesis test for this. And basically, we're going to perform a hypothesis test on the slope to see if we have evidence that not really that the slope is 0.302, but that since we predicted it, we found it was positive, we're saying there's a positive trend or a positive association. That's what our test is for. We want to see, do we have the evidence that this positive trend is there based on our data? So what the beta test does, okay, it's called the linear regression t-test or the beta test, is it basically assumes, it begins by assuming that the slope doesn't exist. And to do that, to calculate that, it basically takes our x and y values and detaches them from one another and shuffles them. And then it graphs this new shuffled set of points and it finds the correlation and slope. I have an animation of that I want to show you, and let me just quickly explain what happens or what you're going to see. You're going to see a line that, or a set of points that are perfectly on the line y equals 2x, correlation of 1. I then am going to shuffle those x and y, basically pulling an x out of a hat and a y out of a hat and pairing them together to give a new ordered pair, and then I'm going to graph that. Let me show you. Okay, so what you see up here is this set of data that is perfectly linear along the line y equals 2x. Okay, down here I have placed those x's and y's into kind of random bins, almost like bingo, and I'm going to randomly pick an x and a y, you can see right there, and just put them together and then graph those over here in a new scatter plot. And then I'm going to do that a bunch of times. I'm going to change the speed so I can just shuffle very quickly. You can see me begin to do this many times. Hopefully you get a sense of the fact that the correlation seems to be 0 and the slope is certainly horizontal. So that really brings us to our null hypothesis. Is the null is that the slope doesn't exist. The alternative will be that it does, and it kind of answers that question on the bottom, which is our original data's slope or correlation rare, or was it common? So that's what our test is really going to be all about, and it's very easily done on the calculator, and in a video coming up, we'll look more at how we would do it by hand. But today, let's just focus on getting the numbers and interpreting them. So remember, our regression equation is an estimator, right? So the hypothesis test really, as I said, is trying to see if this positive or negative association exists. The null, we always begin with, no, it doesn't. It doesn't exist. Okay? And that, again, that was that kind of random shuffling of points. If the points aren't, if it isn't important that x and y are attached to each other, then we would simply get a random assortment of points that have a correlation of 0. Well, we're trying to prove that no, it is important those points are attached. Now, I'm going to put beta, I'm going to put 0, and I'm going to kind of just put a box here because, of course, you can fill the box with any inequality you want, right? Greater than, less than, not equal to, depending on the problem. Now, our test statistic is always, right, statistic minus parameter. This goes back to when we first did z-statistic by hand. We'd say, what did we get minus what the null number was. When we did two sample things, we did sample 1 minus sample 2, sample mean minus sample mean, or sample proportion minus sample proportion. And then we divided that by the standard deviation. So for us, the statistic is whatever the slope estimate we got was, right? For like our example on pulse and height, it was 0.302, minus the parameter, which is 0. It's what comes from the null. And we will divide that by the standard deviation of the statistic, which you can see right here. It is really a form, kind of a manipulation of the correlation formula, and I will come back to how we're going to get this because we don't really ever calculate it by hand. Okay, but I just wanted to point out all of this is on your formula sheet, like so many other things, and it really is still doing the same type of work that you saw when you did the other hypothesis tests. So I'm going back to this height and pulse problem. Our null is that the beta is 0. Our alternative, I just said show that a line, a linear relationship exists, so I chose to do not equal to 0. I certainly could have done greater than, since our slope actually was 0.302. And let me just remind you that the difference in p-values is just doubling or halving, right? So if I change this, whatever my p-value becomes, if I change it to be greater than, I will just cut my p-value in half. all right? So then because it's like this and not two samples, I do have to define the parameter. The easiest way to do it is just say beta is the slope of the population regression equation relating, and then you put your two variables in. All right, the plan step. There are 5 parts to this plan step. I want to talk about it briefly and then tell you, thankfully, that you will not really ever need to worry about them. Let's talk, first of all, we need good data. It still needs to be random. Still needs to be independent, right? We need to be collecting good data. That's what that comes down to. This, we should be checking, if we're doing a linear regression test, we should be assured that the data is linear, that is the best model. We shouldn't be proceeding to the beta test, this test, if a different type of equation would have worked better, okay? So those 3, we're doing the right thing because it's the right model. These 2 are good data. Normal and equal standard deviations. This has to do with residuals. It means that the residuals are approximately normally distributed. Most of the points are close to the line. Some points are a little further away. Very few points are far away. Equal standard deviation has to do with the fact that we want the regression equation to work through its entire length. We don't want it to work really well for small explanatory variables, but then the points get further and further away the further the equation goes out. We want that standard deviation around the line to remain equal. So these 2 things really have to do with the residuals. Here's the good news. The book will always, the AP exam will always say, assume conditions for inference are met. You will never need to check these things because it's a lot of work to check the residual plots and do all that. Okay, let's do this on our calculator. All right, so we go into our good old test menu. Find linear regression t-test. You can see I just put the data here. Frequency I left as 1. Make sure this inequality represents your alternative. This right here is basically if you wanted this equation stored somewhere. You could say go into vars and put y1 and then it would put the equation in y1 in case you wanted to graph it. I'm not going to do that. I'm just going to calculate it. When I calculate it, you can see this output. So you can see a t statistic. Let's write that down. Leave a little room for degrees of freedom. You see a very large p-value. Now, degrees of freedom, it says there are 8. And I just wanted to call your attention to the fact that there are 10 pieces of data up here. And when we first began talking about degrees of freedom, we always said once we have one piece of data, there are no degrees of freedom. That is our entire data set. We gain 1 degree of freedom the minute we add a second piece of data. Well, the reason now, instead of subtracting 1, that we subtract 2 is because until we have 2 data points, we aren't able to draw a line. So it isn't until the 3rd data point that we gain freedom. So for a linear regression test, it is always n minus 2 degrees of freedom. All right? We've been through this part a lot of times. Let me quick write my conclusion. We fail to reject the null because the p-value is too large. And sorry about my sloppy writing here, we do not have evidence of this linear relationship because we are left with the fact that the slope could be 0. If we did this, if we had rejected, then we would have evidence.